let's spend some time reviewing our second unit of the year now, our longest unit of the year, dynamics. We started off, of course, with a definition of dynamics. We said dynamics is a study of motion with regard to what causes the motion. In other words, we talk about forces in dynamics. So if we're going to talk about forces for the full unit, then we better know what a force is. Who can define a force for me? John, what's a force? John was so excited. He knew the answer so well about what a force was. He had two hands in the air for that one. What's a force? Did I call you John? Oh. Sorry, Jack. What's a force? Yes, you do. Well, you still know. Good, Jack. A force is a push or a pull. And of course, we know that there's two things that a force can do. Two effects that a force can have. What's one effect? This is the most common effect, the effect that we usually talk about in Physics 20. This one's a little bit harder, actually, than the definition for force. It can accelerate the object, right? It can accelerate it. And by accelerate, there we go. It can accelerate the object. By accelerate, I mean, we can speed the object up, it can slow the object down, or it can change the direction of the object. Okay, what's the other thing that a force can do? Yep. Yeah, it can deform it, it can change the shape of it. Now, if you get a question on the definition of a force or the effect of a force, you know that's going to be in multiple choice, right? We get 25 multiple choice questions, and we try to predict what kind of questions that we can get as multiple choice questions. Hey, who knows if something like this will appear in the multiple choice? But if it does appear, it's going to appear in the multiple choice section, right? There's nowhere where we're going to ask you, like in a written portion, what are the two things that a force can do, all right? And finally, we defined inertia, which kind of goes along with this whole definition of force and kind of leads us into this next thing that we call Newton's first law. Connor, what's inertia? Oh, were you going to ask a question? Oh, okay. You're going to answer that one first.
Inertia is momentum.
You know what? It's close. It's close. We're going to talk about momentum in Physics 30, and you're going to see that there is a fundamental difference between inertia and momentum, but they're similar.
So inertia would be an object in motion stay in motion.
Yeah. Yeah, I mean, you're leading us into the next thing, which is Newton's first law. But Newton's first law is also called the law of inertia. So if you're saying that the law of inertia, which is Newton's first law, is an object in motion stays in motion until acted upon by an unbalanced force. An object at rest stays at rest until acted upon by an unbalanced force. You're basically saying that an object wants to keep doing what it's doing, right? So we're going to define inertia as what? If it wants to keep doing what it's doing, Hannah, inertia is, yeah, the tendency to resist a change in motion, the tendency to keep doing what it's doing. And of course, we talked a little bit about this way back in February, the end of February, when we were going over this for the first time. Inertia depends upon one thing, whereas momentum, as you kind of compared it to, depends upon two things. Momentum, not how hard it is to change the motion. Momentum would be how hard it is to actually stop something. So momentum is dependent upon mass and velocity, how heavy it is and how fast it's moving. Whereas inertia depends only upon, no. Shape doesn't factor into it. Inertia depends only upon mass, yeah. So we'll say it's the tendency to resist, not resist motion, resist a change in motion. And it depends on mass. All right, that leads us nicely into Newton's first law, which we sometimes call the law of inertia. Because, of course, it's really the law that says things want to keep doing what they're doing, right? An object in motion continues in motion until acted upon by an unbalanced force. An object at rest stays at rest until acted upon by an unbalanced force. So we're going to say in motion, I'll say dot, 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 continues in motion until acted upon by an unbalanced force. An object at rest continues to stay at rest until acted upon by an unbalanced force. Well, by the way, what do we call it? What do we call it when there's an unbalanced force acting on something? What's the term that we assign to an unbalanced force or a total force? It's a net force, right? When the net force is 0, we say it's in equilibrium. If it's in motion and it's in equilibrium, then we call it translational equilibrium. And if it's at rest and the net force is 0, then we say it's at static equilibrium. So if you have a situation where an object is at rest, okay, then the forces must be balanced and it's in static equilibrium. It's not going to move. It's going to stay at rest. If it's moving at a constant velocity, then the forces must be balanced. It's in translational equilibrium, and it's going to keep going at that constant velocity in a straight line forever and ever and ever until it's acted upon by an unbalanced force. So it's acted upon by a net force other than 0. Well, then we went on to Newton's second law, which really amounts to F is equal to m times a, right? It says that an object, the acceleration of an object is directly related to its net force, to the net force acting on it, and inversely related to the mass of the object. So in other words, a is equal to F over m. But usually we rearrange it to take the form of F is equal to m times a. There was a question, a multiple choice question on your dynamics unit test that talked about, I forget who it was that was shopping at Safeway, putting the soup cans in the shopping cart. You guys remember that question? Was it Cody? Cody and who else? Okay, Cody and Shavetta? It's a pretty good memory, actually, if you remember that. So Cody and Shavetta are shopping at Safeway, and Cody's putting soup cans in the shopping cart, and Shavetta keeps pushing with a constant force. And we know that the acceleration of that shopping cart is going to decrease, okay? Because as the mass increases, the acceleration decreases. That's Newton's second law. Now, on the other hand, if Cody didn't keep putting soup cans in there, if he kept the mass of it the same, and Shavetta kept applying a bigger and bigger force, then we would find that the acceleration would increase because the acceleration is directly related to the force. So it's directly related to force. As force goes up, acceleration goes up. As mass goes up, though, acceleration goes down. Now, within Newton's second law, what do you got to be able to do? Well, we solve problems, right? Okay, we solve problems. We're going to use this equation, but we're going to use that equation, F is equal to m times a, in conjunction with all of my other group B equations. So you might get a question that says, here's the mass, here's the acceleration, what's the net force? But honestly, probably not, okay, because that's pretty easy. Okay, if you were to get something like this, it would be more likely that you'd have to use F is equal to m times a to find the force, but first you'd have to get something like the acceleration by using something like this. Delta V over delta T, using this equation, maybe find delta T or something like that. Maybe this equation to find the acceleration, or VF or VI. VIT plus 1/2 ET squared. And then the last one, which is probably the least commonly used one, but still important, it's on your data sheet, VFT minus 1/2 AT squared. So F equals m times a is a standalone equation. We can use it by itself sometimes, but there's a lot of times when we've got to use it in conjunction with one of these group B equations. In fact, when we did F is equal to m times a for the first time, we we kind of made it. We said at the time, well, this is like another group B equation, right? Instead of having 5 group B equations like we had back in kinematics, well, now we got 6 because F equals m times a is just another group B equation. Now, having said that, look, hey, if you've got the mass and you got the acceleration, don't make it harder than it has to be. Okay. Then we talked about friction. Static versus kinetic friction. Static friction, remember, is that force of friction that keeps an object from beginning to move. And kinetic friction is the force of friction that acts on an object that's already moving. So this is the force that acts on an object at rest. This is the force that acts on an object that's moving. And we know that static friction is the weird one. It's the strange one. And it's the strange one because it's the one that varies. You remember that it's not, we say when we calculate the force of static friction, we say that we're not actually calculating the force of static friction, we're calculating the maximum possible force of static friction. In other words, when I do this, when I find this value, this doesn't mean that's what static friction is. It means that that's the maximum that static friction could be. If I was to calculate this value here, FSF max, I was to get 50 newtons, the force of static friction could easily be 30 or 20 or 2. It's just that the most it could be would be 50. Whenever we calculate FSF max, we're getting the most that it can possibly be. And that's why I say it's the weird one. Okay, so let's say that the maximum force of static friction on Ethan's desk is 50 newtons. I apply a force of 20 newtons. Doesn't move. What's the force of friction? 20, not 50, 20. I apply a force of 49. What's the force of friction? 49, not 50, 49. But if I apply a force of 51, well then, if the maximum was 50, and I applied 51, then what happens? His desk moves, right? His desk moves. And then we've got kinetic friction. And when we have kinetic friction, that's easier because the force of kinetic friction is just mu times the normal force. That's not the maximum value, but that's the value if it's moving. So I pushed with 20, nothing happened. 49, nothing happened. 51, it moved. So now I calculate the force of kinetic friction, and I get, let's say, 40. Now I push on it with 51, the force of friction is 40. I push on it with 1,000, the force of friction is 40. As soon as I exceed the maximum possible value of static friction, then that force of kinetic friction will be the same always, no matter how hard I push, no matter how fast it's moving. So the weird one is the one that seems to have a mind of its own. It's the one that responds to how hard I push. The harder I push, the harder it pushes back. But kinetic friction is that force that says, look, I'm going to resist motion, but I'm going to be a constant. Okay, I'm going to constantly reverse motion with the same value as long as the object is moving. All right, here's where it gets, I don't want to say complicated. I almost want to say simple, actually. We've got all these different kinds of multi-force problems that we did. Especially as the year went on, you saw that they were really all the same thing, right? F net is equal to the sum of the forces. That's what this boils down to, right? F net is equal to, I'm going to say F1 plus F2 plus ... That's all of these forces. And I'll tell you right now, okay, I'm not telling you everything that's on the test. We've done things on Thursday when we're reviewing kinematics and already today when we've done dynamics that are going to appear on your test. Yeah, I'm not telling you everything directly that appears on your test, but I will tell you some things. And I'm telling you right now that there is going to be one of these or a combination of these as written response number 4 on your exam. It's either an elevator problem or a pulley problem or an inclined plane problem or just a regular F net is equal to the sum of the forces problem or some kind of combination of those as question number 4 on your final exam. All right, so what do we mean by a regular problem? Well, maybe we just have an object like this, right? Maybe we have an applied force this way, we have another applied force this way, we have friction acting this way, and we want to find the acceleration, right? What do we do there? F net is equal to the sum of the forces, FB plus FF plus FA. Just make sure you keep those signs straight, right? And then, of course, it's m times a. The mass times acceleration is equal to FB plus FF plus FA. In this case, we make FB a negative value, FF would be positive, and FA would be negative. Although some of you like to go the other way around and make left positive, right negative. That's okay, as long as you're consistent. FF and FA have to have the same sign. FB has to have the opposite sign. Connor? Yep. Yep. Well, remember I gave you that really crazy problem with the inclined plane and the elevator and the pulley and the projectile motion? Something like that, except way easier. So maybe you get a pulley problem combined with an inclined plane. Maybe you get maybe a pulley problem combined with, oh, this would be interesting, with an elevator. Okay. Basically, a situation where, though, not crazy hard like that question that I gave you, but the same idea, in that if you can do one thing and you can do the other thing involved, then you'd be fine. Okay, nothing like, I mean, that was insanity, right? That one question I gave you was insanity, and of course I wouldn't give you anything like that on the final exam, but that's the idea. Yep. What are you saying? Your elevator problem is going to look something like this. You got a guy or a girl in an elevator, two forces, always the same two forces acting on that person, the normal force acting up and gravity acting down. Right now I've got them drawn the same length, which means they're balanced, means it's going at a constant velocity or it's stopped. But you know that the normal force could be bigger, it could accelerate upwards. The force of gravity could be bigger, it could accelerate downwards. Bottom line is, hey, what do? F net is equal to the sum of the forces. In this case, instead of FB plus FF plus FA, it would be FN plus FG. And then what do we do next? We say M times A is equal to the sum of the forces. Fn, not the net force, the normal force, plus the force of gravity. See how these two problems are really the same question? Except the first question has three forces, second one has two forces. First one is horizontal, second one is vertical. Okay, same deal though. Fn is positive, Fg is negative. By the way, if I ever ask you in one of these questions for apparent weight, the apparent weight, how heavy something feels, what are we really solving for there? Fn, yeah, Fn. Pulleys. In a pulley problem, maybe it looks something like this. We'll say that there's a 10 kilogram object here and a 12 kilogram object here and a 5 kilogram object here. Let's say that there's a force of gravity acting down here. We'll call it F10. There's a force of gravity acting down here that's a little bit bigger. We'll call it F12. And let's say there's a force of friction. If there was friction, which way would it be acting here? How do we know it's going to act to the left? Well, because the force that's to the right is bigger, and of course we have to count to the bigger force. So we'd say friction is this way. All right, what does this look like? Well, we'd say F net is equal to the sum of the forces. That's going to be F10 plus FF plus F12. And we would say M times A is equal to F10 plus FF plus F12. Doesn't this look an awful lot like the first two questions here, the blue one and the red one? It does, and it should. The point that I wanted to make as we were going through this back in March is that they're all the same. They're really all the same. So I'm telling you, you're going to get one of these or a combination of these on your exam, but they're all the same. Hey, don't make it harder than it has to be. Connor, what's your question?
Is it the mass of the whole system?
Yes, that's a good question. When you're analyzing F10, it would be 10 times 9.81. F12 would be 12 times 9.81. But M right here for the mass times acceleration, the net force is dependent upon all of it. So it would be the whole mass, yes. Okay, so you're good? Yeah. Good question. When you're finding F10, we'd say negative 10 times 9.81 or 10 times negative 9.81. But F12 would be 12 times positive 9.81. Okay, the reality is we do that because even though they're both acting downwards, they're opposing each other. What I sometimes like to do, right, if you remember this, is kind of straighten it out. Right, that means F10 is over this way, F12 is over this way, and that reminds us that F10 needs to be negative, F12 needs to be positive. Or could be the other way around, right? As long as they're opposite signs. And as long as FF is the same side as F10. So it's not so much the 9.81 that you're adding the negative value to, it's the force. We'll make F10 negative, FF negative, and we'll make F12 positive. Okay? And finally, the last one of these is this whole inclined plane thing. Maybe the question looks something like this. Maybe we've got an applied force acting up the hill of whatever. Okay, we've got an angle of 30 degrees. We want to find the acceleration. What do? Well, same deal, right? F net is equal to the sum of the forces. But here, it's a little bit trickier because we've got to combine a couple of forces that don't cancel each other out. We know we have the force of gravity acting down, which is m times g. We know we have the normal force acting perpendicular, and then there's this force right here that we call F parallel. And then we'd redraw it right there, F parallel. So we know that, just like in the other questions, F net is equal to the sum of the forces. F parallel this time plus FA, whatever that is, M times A is equal to F parallel plus FA. Once again, it looks almost exactly like the other questions, right? F net is equal to the sum of the forces. F net is equal to the sum of the forces. F net is equal to the sum of the forces. And F net is equal to the sum of the forces. The only thing here is that we don't know what F parallel is. So we're going to have to find that. Okay? Well, we need FF if there is a force of friction, but I would tell you if there was a force of friction. In a question like this, if it doesn't say anything about friction, then just assume that there isn't one. Yep. Force of gravity always acts down, but the normal force always acts up, perpendicular to the surface. Okay, so it's the normal force. The only time the normal force would ever be downwards is if you were on something like upside down on a roller coaster where the track is pushing you down. But here it's pushing up, not straight up, right, at 90 degrees to the surface. All right, so how do we get that F parallel? Because, of course, in order to do this, we need to know what F parallel is. Well, if this is 30 degrees, then so is this. And we're looking for F parallel, which is the opposite side of that triangle. We're going to say sine 30 degrees is equal to F parallel over the hypotenuse. So F parallel is equal to mg sine theta. You can see here where we could combine a couple of these questions, right? Okay. I'm not telling you that we will or will not combine these questions, but in the end, I will tell you that, again, there's four things up here right now. You know, from the straightforward F net is equal to FB plus FF plus FA, all the way down to the elevator problems, to the pulley problems, to the inclined plane problems. You can see that if you have a couple of them together, it shouldn't make life any more difficult. It's just a little bit more work, a tiny bit more work, that's all. Kind of combining two questions in one. All right, last thing that we'll take a look at today is this two-dimensional forces two-dimensional forces thing. What are we talking about here? Well, we're pulling on things in different directions, right? Let's say we've got an object right here. You're pulling on it this way with a force of, I don't know, 10 newtons. Pulling on it this way with a force of 15 newtons. And you're pulling on it this way with a force of 5 newtons. What do you think of first when you see this? What's the first 5 words that come to your mind here? Ethan? Don't like funny angles. So what do? Just like we did back in projectile motion, just like we did back in those adding displacement vectors problems together, we take it off to the side here and we find the x and y components of that 5 newtons. So we say, over here off to the side, here's x, here's y, 30 degrees, 5 newtons. We say cosine 30 degrees is equal to x over 5. And we say sine 30 degrees is equal to y over 5. And then I like to do this. Some of you guys like to do this as well. And we got 4.33, and we've got 2.5, and we've gotten rid of all those funny angles, right? Now we just have 4 straight, easy vectors to deal with. X and y components. We say the x component of the first one is 0, the y component is 10. The x component of the second one is 15, the y component is 0. The x component of the third one, negative 4.33, the y component, negative 2.5. Can we add those up? 15 plus negative 4.33 is 10.67. Negative 7.5, combine them. And then what do you do with it now? Now it's easy, right? What do we do with it now? Sorry? Find the resultant. Good. And how do you find the resultant, Cody? Yeah. It's the Pythagorean Theorem, right? And then we're going to find theta by using the inverse tan function. Some of you, if you see something like this, will avoid finding theta. Some of you will find the hypotenuse and not find theta then. I'm telling you that anytime you use the Pythagorean theorem, find theta. Anytime you're finding a hypotenuse or a resultant vector, find theta. If it doesn't say find the direction, find it anyways. What's the worst case scenario? The worst case scenario is, oh, you didn't notice that I said what's the magnitude of the resultant vector, and you didn't need the direction. The worst case scenario is you didn't notice that, you found the direction, you put it down, and then you realize, oh, I didn't need to do that. Oh, well, you did some extra work, right? It's better to err on the side of doing too much than not doing enough. So if you're doing one of these questions or anything like this, find theta as well. Even if it doesn't specifically say, find the direction. Force is a vector. It includes direction. Displacement is a vector, includes direction. Velocity is a vector, includes direction. So any of these problems involving forces, velocity, or displacement, find the direction. Isn't this exactly like those displacement problems that we did in Unit 1? Like it's exactly the same thing, right? Except instead of saying, guy walked 10 meters to the north, then 15 meters to the east, then 5 meters at 30 degrees south of west, we got those 3 forces. The only difference here is units, right? Newtons instead of meters or kilometers or meters per second. Good.